now, without further ado, I'll turn it over to Will LaForest and Michael Peacock from Confluent.
Okay, so I'm Will LaForest. I'm Field CTO here at Confluent, and I'm joined by my friend and colleague, Michael Peacock, who's a field engineer, which means, thankfully for all you, he does real work instead of just talking all the time. So, dude, it keeps on going forward. Okay, so what we're going to talk about today is building a dynamic DSL rules engine on top of the Kafka Streams library. So you may hear me use the term rules, routines interchangeably throughout the talk. And that's just because this approach is kind of broadly applicable, both to rules, but more generally to sort of any language that you want to put in there, right? Could even be human language. I'll maybe spend 3 seconds talking about that in the talk. So let me start off with talking about why. Okay, so why would you bother to create a streaming rules engine when there's so many cool and powerful stream processing frameworks out there? So there are a number of reasons. The first is that while all those stream processing frameworks are awesome, they're all general purpose, built to support any domain, tackle any sort of problem. So it's very powerful, but not necessarily optimal for any given problem in particular. So, it's a little bit like those awesome utility knives. They have a knife and a nail file and a corkscrew. If you're lucky, they might have like an interdimensional portal. But as awesome as they are, like if I have a bump bed and I just need to like tighten 100 screws, it's a real pain in the ass. What I really want is just a screwdriver. And the second thing is that while most people here probably, or a fair percentage, know how to code, the vast majority of the workforce don't. Yet there's plenty of important domain knowledge out there that would be really awesome to apply to streams of data. Now, SQL interfaces like Flink SQL and KSQL are great because it makes it a little bit more attainable to non-coders. But SQL is still a pretty general purpose language. And it's actually poorly suited for some problem domains. So secondly, for the usage scenario we're discussing here today, highly dynamic, time-sensitive rules or routines, there are some technical challenges with direct application of those stream processing frameworks. Now first, imagine you express your rules as stream processors. Maybe they're compiled into stream processors. Maybe you can translate them into SQL. Each one has a separate SQL expression. Now, if you have hundreds or thousands of those, that means that each one is consuming the data, each one is deserializing the data, each one is probably producing data, right? Pretty gross. And even if you had the resources to scale for your rules in this fashion, you probably don't want to spend the money. It's just not a very cost-efficient way of going about processing the data. So what you really want to do, if possible, is read the data one time and deserialize it one time, and then apply all your routines. Another challenge is routing data to multiple destinations based upon your rules. So for instance, if you try to translate your rules into SQL statements to route the data, then this is challenging because a given SQL statement is going to produce to one output topic, okay? So this may mean multiple SQL processors. Again, not great for scale, performance, or from a management perspective. What if your rules change frequently? Or when you get a new rule, you want it to take effect as quickly as possible in a domain where seconds matter, right? Cyber is one of those domains. You don't want to have to compile it and then deploy a new stream processing job. Frankly, you don't even want to wait for a new stream processor to spin up. And if possible, you want to try to avoid restarting a topology. Just as we love data streaming, because we get new records milliseconds after they're published, it would be nice if rules can take effect just as quickly. So I'm doing a little bit of foreshadowing here. Okay, so let's talk about how to address the language mismatch as well as the technical challenges. And the first part of the solution I've already alluded to. Okay, so here's the candy bar. This is where it comes in. So most of you probably know what a DSL is. It's a domain-specific language. Does anyone know what this is, what language this is? And you see, if you're born after 1980, you're at a distinct disadvantage.
We got a hand in the back.
Yes! Ah! Oh! Bodily harm to someone, but not to you. Okay, pass it to the gentleman. This is, in fact, Logo, okay? It was created originally in the 60s to help children learn how to interact with computers. Most of the people who are familiar with it know it from their Apple II days, right? So as awesome as Logo is, there's maybe some better examples in terms of HTML, regular expressions, MATLAB, GraphQL, whatever. SIGMA is the DSL that we're specifically talking about today, and it's an example of a language that's focused specifically on cyber data. So think networking data, log data. Now, one way to help with the issue of rapidly integrating rules with low latency is leveraging a tool that's really good at providing changes with low latency. That's Kafka, right? Now, really anything that you can serialize into bytes can be published into Kafka. And if you serialize your rules into a data-oriented format like JSON or YAML or, heaven forbid, XML, and of course it follows that they can be turned into protobuf or Avro, then you can actually treat your rules like data, right? I mean, they are data. You can govern them, you can validate them, secure them, you can transform them, just the way you would your data. So transformation is a great use case. Like, it's good for handling version changes in your language, or an update to a number of languages, or enrichments. So what you see on screen in the graphic is this idea of running a stream processor against your published DSL to produce a new version. The DSL rules live in the same cluster as the data. They are data. And ultimately, what we want to do is join them with the data that they need to process. So this approach helps us deal with the dynamic set of DSL routines or rules, as well as how quickly we can apply it to the data. Okay, so let's go a little bit more narrow and talk about it in the specific domain of cybersecurity. And a little bit of context here. So when Mike and I started this journey, we had a lot of customers doing this. And really, if you take a look at this, it's sort of your pretty typical SOC or SIEM architecture. Lots of logs and network data being collected by vendor-provided agents. So for Splunk, we're talking about forwarders, right? And then being sent to a gigantic store somewhere to support ad hoc querying and reporting, forensic analysis. Now, a few issues arise with this. First of all, SIEM vendors want all the data, or as much as possible as they possibly can get, right? So, and they make their money based upon that. So it doesn't matter what their model is. It could be usage-based, it could be node-based. Like, the more data you put in, that means revenue for them. I understand wanting revenue. But the bottom line for us is they don't necessarily spend a lot of time investing on how to make it easy to send their data elsewhere, right? They want it to go in the index first. Sometimes you just want to use a variety of tools, right? They may not come from the same vendor. Another issue is that threat hunting is really focused on batch processing in these tools. Now, they may try to convince you otherwise, and they can do things like they can try and make it faster by limiting the temporal time that it's being done over, by making it smaller and smaller. But everyone at this conference is probably here because they know that as those time windows get smaller and smaller, and as the number of queries get larger and larger, it doesn't start looking magically like a data streaming engine. What it looks like is actually a crater, right? And I've seen this in practice. So for constant real-time threat detections, they're actually pretty poor. Now, for all these reasons, and actually a bunch more that I'm not going to go into because it's not a cyber talk, it's quite typical to see Kafka introduced as essentially a curation layer for the data. And the idea is to use stream processing both to curate as well as to look for anomalies or detections in the streams before it ever hits a SIEM. You have a bunch of customers doing this. I have a bunch of customers doing it across really all industries, and the government and telecommunications and banking. It's really big. So it's very common. Now, some of the topics will undoubtedly still go to your SIEM tool, right? It's still great for historic analysis, forensic analysis. But you may also want to look for detections directly in the streams of data and then send the matching events and route them to a SOAR or say an RPA system. Maybe you want to start applying machine learning, but it's computationally expensive. You probably don't want to send all the data there. So you want a set of heuristics to determine what you should send there, what's worth examining with a machine learning model. Now this is all great, but recall that some of the drawbacks of stream processing is they expect coding or SQL. And in our experience, it's actually not that typical to have a SOC with data engineers or coders, right? They're really, really good at understanding their domain, understanding how to find threats, understanding the sources of the data, but they're not coders. So oftentimes this is bridged by maybe introducing a data engineer into the team or pairing with a programmer, but that's not always practical from a cost perspective or a resource perspective, depending upon the size of your organization. And if that's not a problem, you may still want to apply hundreds or thousands of independent rules to the streams to do all that sorting and threat detection that I was alluding to. So this is really the problem that Mike and I set out to solve. So enter the imaginatively named Confluent SIGMA, because it's SIGMA and we work at Confluence. But have no fear, it works just great with plain old Kafka as well. It's open source and it's Apache licensed, so we encourage you to hop on, contribute, and join the fight. Okay, so let's first cover what SIGMA is. It's an open source signature format for describing event patterns. Like, we didn't create it, it was just in the environment. It's been out there in this space for a while. And while it could be broadly applicable, right, because it is a rules engine, as you'll see, it's really developed to be focused on security data and security threats. So think logs and network data. And the idea is that the domain experts, so researchers and analysts, can describe the patterns that they've found that has enabled them to detect threats and then produce those so other people can consume it. And so they're reusable both for future detections, but also to be shareable with others. So that, for instance, when the SolarWinds hack occurred, within hours, actually, there was a published SIGMA signature that helped you detect whether or not you was being impacted. So if you had access to that, you could have started applying it, right? So it really builds a strong community of people fighting hackers and cyber criminals. And actually, if any of you saw, there was originally a talk planned here at Current this year with a friend of mine from Ukraine who's out there, fighting the cyber war taking place against the Russians. And part of that talk was how they were taking what they learned there and producing SIGMA rules so everyone could benefit from their struggles. Unfortunately, the Ukrainian government at the last second requested that they not give the talk. So now, these rules themselves are platform agnostic. So you could apply a SIGMA rule against whatever tool you want to use, right? It could be Splunk, it could be Elastic, it could be Sentinel, even grep. Like, I've seen examples of that. It's just someone on the box, like a sysadmin, looking through a log file for something that matches a SIGMA rule. With Confluent SIGMA now, what we do is we allow you to apply it directly inside of Kafka. And then the other benefit is that because it's portable across different platforms, you may have multiple tools you're using. You may be using us for curating the data, but then for forensic analysis, you want to apply the same set of rules, the same SIGMA rules against the historic data as well. That portability is really, really key. Okay, so as suggested earlier, the idea of Confluent SIGMA is to allow people to publish SIGMA rules into a topic and then have those SIGMA rules applied to the streams of data, which are also published into Kafka. So SIGMA rules are then streamed to the SIGMA stream processor, which then joins it with the data being sent to it. The application of the rules are then used to route the data or even enrich it and provide structure to potentially unstructured sources. So some of the SIGMA rules might identify patterns that have a high probability of action being required, like high-risk detections. You could send that to your SOAR. Other ones just represent a set of patterns you want to use to send high-value data to your SIM tool. And then maybe everything else you want to send to something like cold storage. You may not want it now, but you may need it for compliance reasons, or in the future you may discover there was a hack. And so you do want to go back and reload that and take a look at it. Okay, so when Mike and I started this effort, we're like, how can we make it easy to apply SIGMA in streams of data so it's real time? And we spent some time thinking about, do we use a consumer or producer and just make something bespoke? Do we use something like Flink or maybe UDFs inside KSQL? And ultimately, we decided that the Kafka Streams API was really sort of perfect for what we were trying to achieve. Because it's a simple library, we could easily embed it into our application and really let it do all the sort of menial but easy to screw up work of stream processing. And that meant that all we really needed to do was figure out how to map from the DSL, the SIGMA rules, into the Kafka Streams topology. Another thing that we really liked was that we could run Confluent SIGMA as a simple standalone app without a heavyweight cluster runtime. And this means that you can start small on your laptop, but actually kind of importantly for this domain, it means that you can run in the edge, right? It's not uncommon in this space to see small footprints on-prem somewhere. It could be in a manufacturing plant. It could be in a small data center. And what you really want to do is send the data to an aggregate site, but you don't want to send all the data because it's voluminous. What you really want to do is process some of that at the edge. Despite being able to start small, it can scale horizontally with ease. So this crude chart that you see here on the top right shows records per second processed with Confluent SIGMA as a function of EC2 instances. And M2 double extra large, I think is what I used. So with one instance processing, we were seeing 447,000 records per second. With two instances, it was 881,000 records per second. And when we went to three instances, we saw about 1.3 million records per second. Now, in all those cases, it was really CPU bound. In other words, if you looked at the EC2 instances, that was the bottleneck. Okay? It wasn't the rate at which we could read it or anything else. Now, if we had gone to another node, we would have actually saturated our Confluent Cloud cluster, which was one of the multi-tenant offerings. And so it's capped at, it has a quota of 1 gigabyte per second. But again, there's 50 partitions. We easily could have continued to scale this out. And in the future, we may try testing this on a dedicated cluster, but we felt this was enough to show that it scales linear as we would expect it. OK, so I'm actually going to hand things over to Mike to talk about the nuts and bolts of the SIGMA project so you can understand how it works and see it in action. So this is the good part, except for being hit with candy bars.
All right, thanks, Will. That ends the polished portion of the talk here, so now you're stuck with me for about 10 minutes. All right, I'm going to go over a few things. I'm going to give a high-level overview of the project itself, and then a demo, fingers crossed. So the project, I think Will said earlier, available on GitHub, publicly available. We're looking for contributors, so jump in, help out, add features, add some code. If we break down the three components, again, cleverly named SIGMA parser, you can probably guess what that does. Parses the YAML rules. SIGMA Streams, that's really the workhorse of this diesel engine. It's taking all of the rules, doing the storage management, updating, things like that. We have metrics built into SIGMA Streams, and really this is the part where the topologies are created. I'll walk through into topologies in more detail a little bit later. And then a UI, you have to have a UI, right? So we have a SIGMA Streams UI.
I don't need a UI.
Yes, you do. Everybody needs a UI. All right, so let's talk about the topologies a bit. There's really, when you break it down, there's really two topologies. Another clever name, simple topology. What this does is it handles any rules that are just non-aggregation rules. And we'll go over some examples of those. But what this supports is a one-to-many type of rule configuration. So we can have one input record, iterate through all the rules itself, and then output one-to-many different, or zero-to-many rule detections. Now we get to the aggregate topology. It's a bit more complex. It's really more of a one-to-one mapping. So one sub-topology for rules. And the reason for that is that there's a couple things that the SIGMA syntax, our DSL supports, things like group by. So we have to be able to handle a group by capability. has windowing, so we have a sliding window built into our topology. And then the aggregation itself, the ability to count how many detections are seen or triggered before we output to the topic. So again, more complex. The way we're handling that right now is that when you add an aggregate rule or update some of the fields that would cause a rebalance or a reshuffle of the topology, we are stopping that topology, restarting it, or adding the rule and then restarting it. So a bit delay in that, but again, it's Kafka, so there's no data loss. You're just going to pick up from where you left off. We're looking to optimize that, and again, part of the feedback that we're hoping to get from the community here. All right, so if I walk through the topology again, starting with the simple topology, you got the SIGMA rule in the middle there. You got the input data, the record data on the right side. Quick overview of the SIGMA rule. What this is telling us or asking us to do is we got a lot of metadata up there, things like title, status description, and even author. The log source, that allows us to categorize this. So things like product and service, in this case Zeek and DNS, we're leveraging that to say let's filter out the rules that are applicable to this stream processor. So you could have potentially thousands of rules in the mix here. You may only want to say that I want to look at Zeek DNS for this processor and launch another one that's going to look at Splunk, Cisco type of data. So you can have these things scaled linearly. So that's log source. If we look at detection, this is really where we're doing a lot of our matching with the records. The conditional statement is basically saying take a look at that query field in our streaming data, apply a regex pattern, and I want to know if anything is greater than 180 characters. If it is, write it to our output topic. So if we walk through the topology again, we're using flat map values. If you're not familiar with that, that basically lets you take a single record and output 0 to many rules or 0 to many output topics. Again, very applicable to this case. We validate the streaming data against a rule. If we have a match, we'll output it, but we also build in a configuration variable that allows you to say, I may only want to output on my first detection and not all the rules that are applicable. This is something like in a cyber use case that might be applicable to say, I only care about if a detection occurs, but I don't necessarily care about all the rules that apply to that detection.
Yeah, basically that's you're routing data. You have 500 rules. If any of those rules match, I want it sent to my SIEM. You don't necessarily want to check it against all 500 rules.
Right. All right, so once we do detect something, again, quick overview of how we're using our detection results and what we're building. Talked about the metadata and the record data, so we're going to output that to the detection topic. You can see that in the bottom there and some of the other callouts. If the rule contains a regex, we're going to take the fields that are defined in that regex pattern and also output them. So this is key for a lot of things like, I know in Splunk you can build a regex pattern, then extract those fields out. So we took that same methodology. You can build a regex pattern with some mapping in there, and then if a match is found, it will extract those fields and put them in your output topic for you also. So a bit more customization. And along that same lines, if you want to add custom fields, you can do that also. So the bottom part there is what we extended of the SIGMA syntax. So we are compliant with the SIGMA syntax. We didn't change that. We wanted to make sure that was rule number one. But we did extend it to support some Kafka-specific things. In this case, the ability to add custom fields, for example, things like location, source type, and index. These may be applicable to something like analytics or in your indexers like Splunk and Elastic. It may apply there. So it gives you the ability to flex a little bit there. And then the last customization piece is the output topic. So generally when you start a SIGMA processor, you can define an output topic, so your generic output topic, or you can do each rule define an output topic also, so you can route to many different output topics by the rule itself. And then the aggregate topology. Again, iterating through each rule, looking at product service for filtering, validating the rule, and then this is where the complexity really kicks in for this topology. We look at the group by key. So this rule is saying, I want to group by the ID originating H field, right? That's in our streaming data. So do a count based on that field. Count the number of instances in there. There's also a sliding window that you can define in the rule. So that can vary, right? So in this case, it's 10 seconds. And then filter based on the output. So if I do a quick overview of this rule, it's basically saying, take a look at the query field. Again, 60 characters. I want to count how many instances of that occurred within a 10-second window. If it's greater than 10, route it to my output topic.
Broken down by the origin of the connection.
Yes. All right, so enough slides. We'll jump into the demo. Again, fingers crossed, live demo here. The environment we have, I'm running it local on my laptop because they warned us about network connectivity, and so we have a pretty slimmed down version. We're pumping DNS data and Splunk data into our Kafka instance, and then we're applying a couple different SIGMA processors. We have 2 running. We'll visualize it all in the UI. So let's jump into it right now. All right. So let me make it a little bigger. If you're not familiar with Confluent Control Center, it really lets you dive deep into your cluster, lets you view topics, metadata, any kind of metrics. We're really going to focus on the topics itself. So we have a few here. Talk about our DNS data, our output, DNS detection. I want to highlight the SIGMA app instances. So we built some metrics into each one of these processors so you can analyze and visualize some metrics as far as like how many rules it's processing, handling, how many outputs. And then a few others, so that's backed by a Kafka topic. But the important one is the SIGMA rules. The way we're doing our management using Kcache, it's an external project, really cool. What it basically lets you do is build a cache, and then you can use that interactively with your application, but it's all backed by a log compacted topic. So basically gives us a way to manage our rules really easy. But again, every rule will be managed in that SIGMA rules topic. And then our Splunk data. We don't have any rules loaded by default here, so this is the SIGMA Streams UI. Little dashboard up front gives you a number of rules, gives you how much is being processed by our 2 SIGMA Streams apps here. No rules being added, so nothing being processed. We have the ability to look at the SIGMA rules. Again, nothing loaded, but we'll jump in there. And then some of the outputs, the detections, whether it be raw data, and then the detection data for these 2 specific topics. And then we have our processors. Little of the metrics here, again, what they're doing, how often they're updating, how many records, detections, things like that, and their status, whether running or rebalancing.
So essentially, when you spin those up against a cluster, it registers itself every instance. So we can track what the current state of those are, what their health is, et cetera.
And really the purpose of that is like, if you have a highly used processor, it's processing a ton of data, you might want to load balance it in a sense, scale another one, yeah. All right, let's add a simple rule. We'll show how it's working interactively here.
So the narrative here, I'm just going to add the narrative.
Go for it.
So we actually had a colleague that did a data exfiltration exercise where he was taking Moby Dick and he was exfiltrating it by doing DNS lookups. So when you hit a DNS, it makes a call to a DNS server. Well, there's a query string, and he was base 64 encoding this text in there. And on the other side, he had his own interception of the DNS. And this is a legitimate tactic that can be used. So these rules are really about how would you go about detecting this taking place in DNS data.
Okay, thanks for the context. I forgot all that story, so good.
Who doesn't like a good story?
Okay, so walk through the rules. I think it touched on this one earlier. Again, we're going to focus on that detection portion. We're going to look at the query field and anything that has greater than 180 characters, we're going to throw out and route to an output topic, DNS detections. So I will publish the rule. Let me go back to the Confluent Control Center. I'll show you that it's in the SIGMA rules itself. There you go. So now it's backed by that Kafka topic again. All right, let's go take a look at the detection output. What you have here in the graph is, anything in gray is the raw data. So this is streaming through. Any detections we see would occur, and you'll see it in the output in red there. But you can see we're not detecting anything. 180 characters is pretty big, right? So we don't have a lot that are.
Most hackers are not that dumb.
Yeah.
Right? They're not going to make it more than 180 characters.
So just to show the flexibility of the rules here, I'll update it real quick and just mark it. They'll do 18 characters just to see that it's updating in real time, and then it's being applied to that data, DNS data. So publish the rule. I'll come back. And now we see a bunch of detections being occurred, right? Anything in red. And the idea of this is all that red is really the meaningful data, the real data, and you don't want to really waste your time with that gray data. So filter it down, aggregate it, and then push that to your tools of choice. Okay, 18 is a little too low, so let's go back and update it. But again, what we're showing here is that you can interactively work with the Kafka Streams app with your DSL.
Now, note that while we're publishing rules from this user interface, it's kind of immaterial where they come from. So there's a company called SOC Prime. Their business model is actually producing this content, Sigma rules, that you can subscribe to, and you can integrate with them. So like if you have a subscription, then you could be taking those rules and publishing it straight in. So like, if you think about it, straight from detection, SolarWinds hack, 2 hours later, they publish it, it's immediately detecting in real-time streams. Pretty cool.
All right, let's get more of the aggregation rule. Again, it's a little bit more complex. We do have to start and stop the topology. Looking to optimize that.
We don't manually have to do it.
No, it's built in.
For you, but.
Yeah. All right, a quick walkthrough again. Looking at a query field. In this case, we're going to count how many detections we have. If it's greater than 10, within that 10-second time frame, we'll output or route to our output topic.
So the idea is it's a little bit long because I'm putting little pieces of Moby Dick over a period of time, right? But I wouldn't detect it in theory if I just looked at it at any point in time. Like 60 characters is not that bad. But consistently, then that's suspicious.
So again, because it's an aggregate, we have to restart the topology. So you see the status here is rebalancing. It's pretty quick. It just depends on how long you're down for that rebalance to finish. But typically it's not a long time. So let's take a look at our detections. Hopefully we start seeing some. What was the
window?
Mr. Haha, is that what it was?
Mr. Haha, yeah.
Was it on our exfiltration?
Yeah.
Let's see what the status is there. Still, there it goes, now it's running. There we go, we start seeing the detections. If we look at the data itself, you can see that it's at DNS exfiltration time, has the source data applied to it and some other metadata associated with it. So.
And the query string, that's Moby Dick.
Yeah, Mr. Haha. All right, so again, it's comparing that raw data to the output data. Again, that's the red data is like your meaningful data, really what you want to analyze and focus in on. I'll show the processes again. We start seeing how many are being detected here and how many are being processed. So this is updating in real time. And then one more, I'll show the regex. Let's take a look at the regex pattern. We talked about this earlier, but just again, to reiterate, we're taking any regex pattern, mapping those fields, and those mapped fields, in this case you see timestamp, hostname, will get pushed to the output topic. We also have the custom fields and then a dynamically defined output topic called firewalls.
I don't know, like in the field, I don't know how many times I've been asked, hey, do you have a Grok stream processor? Because that's the common pattern, right? Well, this is effectively that. So.
We'll take a look at our SIGMA rules. We got 3 now. Take a look at the firewalls, output topic, and there you go. So you can see the custom fields there, the map fields are all part of the output topic. And then I'll just show, again, just the dynamic nature of it. I'll update it. I'll write it to a different output topic. It's getting applied to the stream again. So anything where the rule gets applied from there on out, it'll get written to a firewalls test topic. Publish it. Go back to C3. I'll show you the topic there.
Okay, so first, I guess some general considerations when you're talking about DSL stream processing, aside from SIGMA. The first is, if you're going to do this, you really need to consider how you're going to handle newly arriving rules, right? Do you want to apply it just to the unprocessed messages, like in other words, new ones coming in, or do you want to go back to the beginning, right? And if you're going to go back to the beginning, how are you going to handle that? Now, for the SIGMA domain, for the cyber domain, you already have historical data going someplace. So typically, that's not an ask that we've got. Can you start at the beginning? But if you did, there's sort of 2 ways you can approach it. One is you can spawn a separate app, or you can actually create a new topology. And then there's an optimization that we've been playing with, where effectively we wait for that to catch up to the other topology. Then when it does, we then synchronize a merging of the two topologies and start it back up. And remember, the whole idea is, how do we minimize the number of times we're reading data? So that's what that complexity is all about. The other thing I want to point out is a new feature in Kafka Streams, which is super awesome, and that is our version state store. So what this means is that for an aggregate, for a table, it doesn't just keep track of the last value. It actually has previous versions as well, temporally. And so if you have late arriving data, you can actually apply it to the rule that was there at the time. Or it doesn't have to be a rule, it could be another stream processor. But in our case, it would be a rule. So imagine we have late arriving data based upon some timestamp, and if the rule is important, of which one it's applied for, this is going to make a big difference. We won't be able to implement this until KIP 960, 968, and 969, because we're doing essentially a customized join. And so we need to be able to query this version table, and that's not supported for interactive queries yet. So pretty cool. In our domain that we're talking about doesn't matter, but you can imagine a domain where you're processing financial transactions. And if the rules in which you treat a transaction changes, you better make sure you're using the right version at the time of the data, right? Another thing is, consider how the separate rules or routines may interact with each other, okay? SIGMA, for instance, that DSL doesn't support the notion of priority or dependence. We may add that in, but other DSLs may. So you may have a scenario where you have a group of rules. If it matches, then, this is if this, then that, you want to then go to the next set of rules. In that case, you want to look at using the processor API to sort of create a DAG based upon sets of rules. Not something we've done, but it's something that you could do with your own DSL builder. Which leads us to the what's next part. So first of all, we have a roadmap, which is Kanban boards in the GitHub project that shows you sort of the things that are in process, the things that we think are coming next, and the things that have been completed. So any ideas we get from the community, we put in there so we can track them. The biggest thing is we are refactoring all the scaffolding and the work that we've done so that anyone can take this and simply implement their own builder class for their DSL, whatever it is. So I think Anna, I don't know if she's going to use her project or not, but she's working on a Morpheus stream processor. She could create a DSL based upon that spec. But there's a lot of other specs out there. So that's just to make it easier for people to do the same sort of thing, create their own DSLs as stream processors. And one of the things that we toyed around with is actually making a large language model stream processor. There's no reason why you can't. You publish the prompts in there, you then construct a topology based upon that, and then you run that. So now we've taken it to the next level. You don't even have a DSL, you just have the prompt to describe what you want to do with the data. It's pretty practical, actually. We played around with it, but overcome by events so
I think
far.
we had to add LLM in this talk anyway. So
Yeah, you had to. Otherwise, no one would show up. OK, optimizations is a big one, right? First of all, we want to do some aggregations on the topology, the aggregate topology. And this means essentially that we want to bin based upon key and time window. Because if they share the same key and they share the same time, we should be able to share the same topology and then apply the rules in a similar fashion that we're doing with the simple topology. We also need a more graceful way of managing the aggregate topology chains. Mike alluded to this right now. If you get a new rule or you change an existing rule that changes like the window, it means stopping and restarting the topology. It's not very graceful. It's a little bit of a free-for-all. It's been working on our testing, but I was talking to Matthias earlier. I was like, yeah, we don't generally recommend that. So there's a couple different ways we can do that. One of the ways is to do a self-coordination amongst our stream processors, which, as it is now, we can track the state of every other processor, so we can wait until they all quiesce at a stop state, and then do a controlled start across them. But there's some other ideas we've been toying with. And then honestly, we just need to do more general profiling and optimization. So the numbers you saw there, that's just kind of unoptimized. right? We haven't done that much work around that, saying where can we fine tune it. Most of the work is really that pattern matching, that sigma that we've taken and embedded into the topology. We'll probably switch also to a global K-table from K-cache. K-cache is really cool, but when we switch to the global K-table, that allows us to do that historical rule matching. So that should be pretty cool.
Mm-hmm.
All right, well, I appreciate the interaction. You've been a great audience, and hope to see you around.
Thank you.